Well, good morning. This is Wednesday morning, the 22nd of March, 2017, 8:07 in the morning. It's supposed to be linear algebra, math 237. However, I'm the only one in the room, so I don't know if folks are taking spring break early or what, but I guess we'll get going today with nobody here. My memory is that we are in Chapter 3, of course, determinants, in Section 3.2, determinants in elementary operations, on page 114, just about the middle of the page, example 3. Okay? Now, here's what the question asks for. Here is matrix A. 3 by 3 matrix, -1, 2, 2, 3, -6, 4, and 5, -10, -3. Okay. It says find the determinant using the elementary column operations. Okay. We could do this by expanding this, repeating the first two columns, and doing your down diagonals, adding those. Okay, good morning. So glad you're here. Get bored talking with myself. It's pretty conversationalist, you know. So, and then it's here. Okay. Yeah, flip them if you'll flip the lights. Yeah. Thanks. I think you probably heard all the announcements. The only things to note, especially if you are interested in the Lawson State Academic Scholarships, the deadline for this is April, probably the 17th, because I think the 15th falls on a Saturday. So I imagine they're going to have it be Monday the 17th. Not absolutely certain of that, but the deal is next week is not much of an option to do much. Maybe you could take it home and do it, but you won't get any signatures here or other things here because no one will be here. This Executive Women International Assistant Scholarship Program, which is adult students in scholastic transition, that deadline is Friday, April 28th, so you have a little bit longer on that. And then the other down the road, you know about those. All right. We were asked to find the determinant of this. Okay? And of course, one way would be repeat the first two columns and do your down diagonals, multiply those, and your up diagonals, subtract those from the products of the others, and see what you get. They're suggesting that we do it with elementary column operations. Now, elementary row operations would work too. If you were going to do elementary row operations, of course, the first thing you do is change the sign of that. That's going to change the sign of the determinant. Realize that. And then the next thing you would do is row reduce this and that, and you would come up with a triangular matrix pretty quickly that way. But what they're suggesting is use column operations, and if you do this one and that one, I think you'll see things happen very quickly. And in fact, in this one, don't even change the -1. You didn't have to on the other one, and probably it's a good idea not to, because remember, you don't want it necessarily in row echelon form, which is all ones down here. No, you don't really want that. You want just diagonal elements. So let's try doing a column operation. Which one would you suggest? Since I let on that much. To get you some zeros somewhere. Just like elementary row operations, only do an elementary column operation. The key here is look at the first row, second row. I mean, first column, second column. Yes. Yeah. So 2 times column 1 plus column 2. Exactly. And let's see what that becomes. Okay. Now remember, that's the elementary row operation that does not change the determinant at all. Right? Okay. So when we're doing that, and we're finding a determinant, so I'm going to also transition this to a determinant. So we're leaving the first column alone, -1, 3, 5. And the new second column is what? 0. 0. Are you stuck? You know what? 0. Okay. And I can write down the third column if you desire. 2, 4, -3. Jonathan's here. There you are. Okay. Jonathan's top of the alphabet in this class, and in my other class he's next to the bottom. So just crazy the way the alphabetizing does here. Now, can you tell me anything about the determinant of that matrix now? That's all we're looking for, is to find the determinant. What would be the determinant of that matrix in that form? Okay. But I think you were here when we said you could choose any row in any column and do your determinants from that, right? Or were you not here then? Maybe not. Okay. Hint, choose a row or column with a lot of zeros in it. Okay, remember? Okay. Does one of these fit the bill? Which? Second column. And what happens if you go down that one? In fact, the determinant is 0. Because you do 0 times this minor, that's going to be 0, plus 0 times this, or minus 0 times this minor, it's still 0, plus 0 times this minor, and it's still 0, plus minus 0 times this minor, and that's still 0. Everything's 0. This is, the determinant of that matrix is indeed 0. Okay? What does that tell you about it? That is the determinant Second? Singular matrix, exactly. There is no, if that were representing something else like system of equations or something like that, no solution. I mean, there'll probably be infinite number of solutions. Okay, not a unique solution. Okay. Okay. Now, there's another. Now, this linear algebra applied at the bottom of this page is a pretty interesting one, at least in our household. I can never work a Sudoku, because my wife always gets to them first. Okay, she always has them done before I even get to look at them. Okay, but this is an interesting little blurb here in the number placement puzzle Sudoku, I guess is how you say it. The object is to fill out partially completed 9x9 grid of boxes with numbers from 1 to 9, so that each column, each row, and each 3x3 subgrid contains each of these numbers without repetition. For completed Sudoku grid to be valid, no 2 rows or columns will have numbers in the same order. If that should happen in a row or column, then the determinant of the matrix formed by the numbers in the grid would be 0. So that's a direct condition, result of condition 2 of theorem 3.4, which is coming up later on the next page. So, if you thought, oh, what's another way to do this Sudoku grid? Do a determinant. Okay, no, I'm just kidding. You would want to do that, but you could. So let's do page 115, matrices and zero determinants. Example 3, that we just did, shows that when any two columns of a matrix are scalar multiples of each other, just like we knew if any two rows were scalar multiples of each other, the determinant of the matrix is 0. That's one of 3 conditions that yield a determinant of 0. And here's what they are. Theorem, okay, Jonathan still doesn't have a book, so I'll write this down. Theorem 3.4, conditions that yield a 0 determinant. If A is a square matrix, why does it have to be square? You can't take a determinant of anything that's rectangular if it's not square. If A is a square matrix and any one of the following conditions is true, then, and I'm not going to write all that, then what we're going to get is the determinant of A equals 0. Okay? I left off the middle part. Here's the middle part. An entire row or column consists of zeros. Okay, that's what we wound up with in that one. Example 3. If that's the case, stop right there. Your determinant 0. Okay? Any two rows or columns are equal. Then you multiply -1 by 1, add to the other, you get a row of zeros or a column of zeros. Okay? Number 3. One row or column is a multiple of another row or column. That's what we just had. One row or column multiple of another row column. Okay. If any of those happens, your determinant is 0. If the determinant is 0, as Emmanuel said, you have a singular matrix. Even though it's a square matrix, you cannot find an inverse for that matrix. Okay, so let's do another somewhat similar. Any questions on this before we move on? Okay. All right, example 4. Find the determinant of this one. A, again, is 1, 4, 1, 2, -1, 0, and 0, 18, 4. And Marcus is here. Just missing Nigel, which is fairly unusual because I think before today, wait. Second? 18. Yeah. Well, wait, let me see. Yeah, 18. 0, 18, 4, is that what you mean? Yeah. Nigel, I guess, missed last Thursday too. Okay? That was the first day I'd missed. This is, if he doesn't get in today, it's the second day. That's all term. Okay. So, here we have a matrix. And what we're asked to do is find the determinant of that matrix. Now, if you had maybe another 0 or 2 in there, pick a lower column that has a lot of zeros. Right now, you have 1 0 in 2 rows, 1 0 in 2 columns, but nothing with any more than that. You could proceed with any one of those and do your regular thing. You could expand it by repeating the first two columns and do your special deal with the 3x3s. That only works for 3x3s, by the way. Or you can try a row or column reduction. But frankly, just looking at this, I don't see any of those that are going to be particularly handy. So, you tell me what you think we ought to do. We could triangulate the matrix. That would work too. That would be a possibility. So, have a preference. Have several options before you. You choose. That was the problem on the test, homework exercise. What would you do to do it? What would be your approach? Choose something. You got a lot of choices. All of them are pretty straightforward. None of them are any harder or easier than the others, I think. So pick one. Okay, and just go down the first column and do it. Not a bad choice. Okay, so the determinant of this then, we'll change this to a determinant. Just imagine that the bracket isn't there, and that would be what? You're going to use the first column. So basically, I'm going to wipe out the first column with a light colored line here, and then we'll start with the first element. What is the sign of that position of that element? Positive. So it's going to be a 1. It is a 1. I mean, positive 1, so I'm not even going to write it down. So let's wipe out first row, first column, and it would just be the 1 times the determinant of the one in here. And I'm not going to write it down again. You can just do it right from there, can't you? And what is the determinant of that 2 by 2 now? -4. Okay. And Emmanuel chose to do the column 1, right? That's what you, okay. And get these out of the way too. So let's go to the second element. Okay, what's the position of that? That's a negative position. So that's going to be a -2 times the determinant of what's left there. Can you do it just from there? Determinant of that? Second? A little louder. -2? -2 times a -2. Everybody see what he did? Okay. This is a negative position, plus, minus, plus, you know. It's a negative position. You wipe out the first row, first column. Second row, first column, because that's the position you're using. And then you do the determinant of what's there. 4 by 4 is 16, minus 1 times 18 is 18. So 16 minus 18 is -2. -2 from the position, minus 2 from the determinant. Okay? And finally, I think I can do the last one. 0. Okay? So we're not even going to write that. So what do we have as our determinant? -4 plus 4 equals 0. Whoa! Okay? So that determinant was 0, even though, okay, entire rows weren't equal. No, entire rows weren't 0. No entire rows or columns were equal to each other. And no entire rows or column was multiple of each other. Okay? So none of the three things fit, but that didn't say it was necessary. It just said if any of those happen, you know you have a non-zero. So I agree, this is a pretty easy way to do that determinant. Okay? You had simple numbers, a 0 in there. That's probably easier than expanding 2 columns and doing the down diagonals and up diagonals and that kind of stuff. Okay? So, let's see how the book did it. They chose to do a row reduction on row 2, which is fine. It doesn't change the determinant any. -1 times first column, -2 times the first row plus the second row is going to make a 0 here. Okay? So when you have that, then you have a 1 there, do the determinant there, you will get the same thing. I think this one's just as easy, probably easier. Okay? So, either way works. But, when they did that, not only did they get something pretty simple, but the other thing is, then they wound up with the second row. The third row was a multiple of the second row. So then you could tell it was 0 without even doing any calculations. So 1 row reduction or doing like the manual did. Either one will work. Now, that may lead you to wonder, what is the easiest way to do a problem? Example 4, you could have obtained a matrix with a row of all zeros by performing an additional elementary row operation. And you could do that, but as soon as you saw they were multiples of each other, you didn't have to, but you could have. You have now surveyed 2 general methods for evaluating determinants. Of these, the method of using elementary row operations to reduce a matrix to triangular form is usually faster than the cofactor expansion along a row or column. If the matrix is large, then the number of arithmetic operations needed for cofactor expansion can become extremely large, okay? For this reason, most computer and calculator algorithms use a method for involving elementary row operations to get it into triangular form. Once it's in triangular form, just multiply your diagonals. Okay, that's all. The following table shows that the numbers of additions plus subtractions and multiplications plus divisions needed for these 2 methods for matrices 3 by 3, 5 by 5, and 10 by 10. Okay? Now, 3 by 3 matrix, cofactor expansion, additions are 5, multiplications are 9. That's additions and subtraction, multiplication, and divisions. Whereas row reduction, 5 and 10. So sure enough, cofactor expansion works. Is the easiest way on a 3 by 3. Okay? Now, when we have a 0 in it, even easier. Okay. Look at a 5 by 5 though. 119 and 205 versus 30 and 45. Give me the row reduction on that one, okay? Much simpler. 10 by 10, 3,680,000, blah, blah, blah. 6,200,000, blah, 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 1,000. Multiplications, additions, multiplications, still big numbers, but nowhere close to millions. 285 and 339. So, row reduction, anything larger than a 3 by 3, unless you have a lot of zeros in it, okay? Or you have one of those cases where you see a row or a column as a multiple of another, or something like that, then by all means use row reduction. In fact, the number of additions alone for the cofactor expansion of an n by n matrix is n factorial minus 1. Yeah, right. Okay? Y minus 1. N factorial would be enough. Okay? So 30 factorial, okay, would be 2.65 times 10 to the 32nd. I don't want to go there. Even a relatively small 30 by 30 matrix involves 10 to the 32nd addition operations. Remember, just addition, okay? If a computer can do 1 trillion operations per second, it would still take more than 1 trillion years to compute the determinant of that using cofactor expansion. Let's not say we did, okay? Yet row reduction would take only a few seconds. Let's go with row reduction. When evaluating a determinant by hand, You sometimes save steps by using elementary row or column operations to create a row or column having zeros in all but one position, then using cofactor expansion to reduce the order of the matrix by 1, and that's what we just did, basically. Okay? So they're going to show this again. This is another one. I think I'll delete this and do a new page. Here's matrix A. They love the name of A. Okay, -3, 5, 2. 2, -4, -1. And -3, 0, 6. Okay? Now, first thing always to do is just do a quick glance to see if any rows or columns are multiples of each other. Right now, I see none. Do you? No. None at all. Okay. Now, what might be an approach here, though? You could do, and again, 3 by 3 is going to be just as easy if you do the cofactor expansion. But you might save some effort if you choose something else first. Does one row or column expansion reach out and grab you? Now, here's the other thing. I guess I should say this. Really, the first thing I look for is what? 0. We got 1, okay? It's in a column that's 5, -4, 0. But it's in a row that's -3, 0, 6. Now, anything strike you about that last one? Yeah, that's a multiple of this. Now, not the whole columns, but at least that is. So if we do a 2 times this and add it to that, that doesn't change your determinant, right? Okay? But it gives you a 0 there. So let's do that first. Okay? So 2 times column 1 added to column 3. Okay? And since we're going to do determinants, let's go on and do that first. We'll keep column 1 the way it is, -3, 2 minus 3. We'll keep column 2 the way it is, 5, 4, 0. No, -4, 0. Okay, watch those signs. What's your new column 3? Okay, we're doing, because Emmanuel noticed that this is twice that. Like, well, absolute value-wise. Yeah. Okay, so if you multiply this by 2 and add to that, that becomes a 0, right? Because that happens, we got a 0 here. We don't want to mess with that 0. We love to keep our zeros. Okay, but to make that a 0, we're going to use this column operation. Now, you don't do this if you're doing matrices, that your systems of equations and stuff like this. This is just for determinants. You can either use rows or columns for determinants. And we're doing this elementary column operation, which is multiplying this by 2 and adding it to that to give you a 0 in that last position. But we need to do the top 2 as well. So what do we get?
2 times -3 plus 2.
Right? It's what? -4. Got it. Next? 3. Next? 0. All right. That's what we wanted, folks. Now, let's use that third row and do your determinant. Now, first, what position? Okay, we're using the third row here. And we're only going to need this first one because those 2 are zeros. So you got one series of operations to do. What is the sign of the position of the negative 3? It's a positive position, so we leave it minus 3. And then we do what? Take the determinant of what's left. And what's that? Okay, do the down diagonals first. 15. Okay, minus, because when you do down diagonals, it's negative. It's net minus a plus 16, so that would be minus 16. And that's going to be negative 3 times a negative 1, and that's going to be 3. There's your determinant. Okay. Not too hard. One elementary row operation gives you a column row with all but 1 0. And just do your row reduction of that. Pretty simple. Okay? That's exactly what they did, and they got the same answer. Good for them. All right? Boy, this isn't bad, is it? Let's try to do a bigger matrix. One of those 5 by 5s. Here's your new A. 2, 0, 1, 3, negative 2. Negative 2, 1. 3, 2, negative 1. 1, 0. Negative 1, 2, 3. 3, negative 1. 2, 4, negative 3. Didn't come down far enough here. 1, 1, 3. 2, 0. I can almost hear it now. Ooh, yuck. Okay. No, y'all don't have to say that. Okay, what do you look for first? Look for the zeros. Where do you see the best collection of zeros? Second column. Okay, and what makes it even better? You got a bunch of 1s there too, and that's going to be easy to work with. So here's what I would suggest. Or what would you suggest? You tell me. Okay, here's what I would suggest. How about adding these 2 rows and those 2 rows? That gives you a 0 here. That gives you a 0, one of those. So why not let's keep the 4th row and do those operations. That will give you all zeros except for that minus 1. Happy with that? Now, second. Yeah, if you add these 2, it's going to wipe out this one. Add these 2, it wipes out that. So, but really, time out. We really should do something else first. We should check to see if any of these are multiples of each other. Certainly, this one isn't multiple of any other because you'd have zeros in it. And this one and that one couldn't be either because you'd have zeros. And this one, oh, let's see. Yeah, no, those 2 can't be. So, the only ones that we have to worry about are these, nope. Those, nope. These, nope. These, nope. And these. Yeah. None of these are multiples of each other, so we really should always look for that first. So, you want to do, and I'm not saying this is the best method, it's just the thing that strikes me. We'll use this row to eliminate the 1, 0, make zeros in those 2 positions. So, and we're doing a determinant. That's what it said, do find the determinant, so that's what we're finding. So we're going to leave row 1 alone. 2, 0, 1, 3, negative 2. Okay, now I hope y'all are checking and make sure I didn't make a mistake writing it down. That would be tragic. Okay, let's add these 2 rows together. This is row 4, 4 plus row 2. Okay? And what would that give us? You do it. Yeah. See, by adding these two together, you make the 0 here. See, that's going to be really easy to do, right? Okay?
Okay, so 3 and negative 2, 3. Maybe that's
1. Continue. 0. You say 5? Okay.
2 plus 3, right?
Yep.
That'd be no, 1.
2 plus 3. Okay, good. Yeah. 6. Negative 4. Okay. What's that? Yeah, right. Okay, let's write down the next row. It's already got a 0 there. 1, 0, minus 1, 2, 3. Okay? And we're going to leave this row alone. 3, negative 1, 2, 4, negative 3. Okay? And what's the new 5th row? Row? That's what we're doing. Okay, you could do that. You'd rather do that?
No, I was just asking.
Yeah, you could. The reason I did is just adding these two makes a 0 there, and adding these two makes a 0 here. But it also would make one there. But it just is keeping me using the same number. But you don't have to. You could have done it the other way. You're absolutely right. If you see there's an advantage of it, we'll do it. But since I've already written that, I don't want anything else. Okay? If you see an advantage, I certainly will.
No, I was just asking.
Okay, yeah, you could have. You certainly could have. So here we got row 4 plus row 5. And what does that become? These are a little easier. They're right next to each other. 4, 0, 5, 6, and what? Negative 3. Okay. Now, now I like to pause again. See, we certainly have somewhere to start here. Okay? And maybe just to cut down on the eye fatigue, because you sort of have sensory overload here, let's go on and write the remaining matrix. Okay? So, first thing I need to know, what's the sign of that position for that negative 1? Positive. So that's going to be a minus 1, because it's positive of minus 1. Now let me see if I can get this other one written correctly. 2, 1, 3, negative 2. 1, 5, 6, negative 4. 1 minus 1, 2, 3. And 4, 5, 6, negative 3. Did I do it right? See, basically what I did is this negative 1 times, wipe out this column and that row, what's left. Okay? Did I get it right without changing any signs or mixing up numbers? Okay. Now the big boo hiss here is no zeros anywhere. Yuck. Okay? But I want to check and make sure those two columns are multiples, the rows are multiples of each other, and those two columns are multiples of each other. And I don't think either will be the case. Okay? Now, you get to do whatever you want. What would be your suggestion? It's up to you. Now, remember, we're not trying to go to reduced row echelon form, not even necessarily trying to do a triangular matrix, so that is an option, what would you suggest? Anything that reaches out to grab you there? You can do anything you want to as long as it's legal in most states. I don't know if this is going to be particularly helpful, but I look at this and say, well, let's add these two rows together. You're going to wipe out this, and let's add the -1 of this to this one and wipe out that one. You're going to wind up with 2, but you'll get 2 zeros in there, won't you? And that'll be better than none, right? So let's try that. Again, you're not trying to do row reductions the way we did before. Let's just do what seems like it might make sense. So let's do row 1 plus row 3. Okay? Now don't forget you got a -1 there. Okay? All right. So we're using row 1, 2, 1, 3, -2. And right now we're not going to mess with row 2. But let's go to row 3 and do that. Row 1 plus row 3. What does that give you? 3. Yeah. 0. 5. 1. Okay. Now, it really sort of doesn't matter what you do next, but I would be tempted to do minus row 2 plus row 4. That will wipe out the 5 here. Leaves your 1 there and wipes out that. So, okay to try that? So what does that give you? Minus row 2 plus row 4. Yeah. Okay, we're using row 2, so let me write down row 2. 1, 5, 6, -4. Okay, and that will be a 3 down here, a 0 here, a 0 there, and a 1 there. Okay, some unexpected consequences there. Okay? All right. At this point, you're down to really, in a sense, 2 by 2, so you don't really have 2 by 2, but you're pretty close to it. If you do either this column or that row, you only have 2 really operations to make. You want to go for one of those? Or do you want to keep kind of reducing? Actually, one step will get us down to only 1. You see what that would be? Yeah, these 2 rows. Like, minus this plus this, you'll wipe out these 2. You'll lose this 0, but you keep that 0. So you want to do that? That's a pretty easy operation.
You do minus row 3 plus row 4.
You could do it that way. The only thing is that gives you a -5 here, and I like +5.
Oh.
No,
So what you're saying is to...
it's just my little thing. The more complicated, I'm going to operate with the simplest row on the more complicated row.
That way your 0 stays 0.
Yeah, this one does. That one doesn't. Yeah, that stays at 5. Yeah, but you're right. That stays at 0 down here. Whereas the other way, that won't. So yeah, So, what did we decide? We did, huh? Minus row 4 plus row 3. Is that what we did? Use the simpler row to kind of reduce the more complicated row. Okay? Now we still got the minus 1 there. Don't forget the minus 1. Okay. And then what do we have? We're not going to mess with row 1. 2, 1, 3, minus 2. We're not going to mess with row 2. 1, 5, 6, minus 4. Okay? But what we are going to mess with is row 3. And what does it become? What's that? I couldn't hear, sorry. Yeah, we're changing row 3. I'll go and write down row 4 so that we know that. 3, 0, 0, 1. Okay. What's our new row 3? 0, 0, 5, 0. Okay, I think I'm ready to rumble. Okay. I need more room, though, to rumble. So if it's okay, I'm going to go on and erase my original row up here, original matrix. Are y'all okay with that? Okay. Here it goes. Going. In the process of getting gone. Okay. All right. Mike should have done the other two, but let's just do with this. Don't forget your minus 1. Okay? Now, what are we going to use on this one? Row 3. I'm going to go on and draw a line through it. Okay? Very light colored line. Right there. Okay? So, how are we going to use that? The 5. So let's go and get rid of that as well. Okay? Now, next question is, what is the sign of that position? Positive, because it's on the diagonal. The diagonals are always positive. Good catch. So that's going to be a minus 1 times a 5 times the determinant of what's left. And here's what's the determinant of what's left. 2, 1, negative 2. 1, 5, negative 4. 3, 0, 1. Okay. That's an ugly 4, isn't it? There's lots of ugliness there, okay? I think you can make out most of the other ugliness. Okay. Again, I look for my 1, I see it. I mean my 0, I see it, only got one of them. And, ooh, I do see something that could simplify a little something. Do you? We could, go on and do the calculation here. You've got 1 0 in there. It's not going to be really bad. Or we can do one more row reduction. It's up to you. Actually, when you get down to 3 by 3s, just about as easy going with it, right? Okay. So you choose either a row or a column to do your cofactor analysis. I really don't care too much. I have a little bit of a preference, but not a lot, which you want to use. There's 4 I want to eliminate completely. What do you look for? 0, and you got 1. So that means that 1 column, column 2, or 1 row, row 3. Your choice. Which? Row 3, is that what you said? That's what I like too, okay? So let's do that one. I think I'll wipe out this other one over here too, if that's okay. We shouldn't need that anymore. Now, the thing is, I just hope I haven't made a dumb mistake somewhere. Okay, so let's expand that. Okay, don't forget your minus, well, let's go on and multiply together. That's a minus 5, so I don't have to write them down. Okay, now, we're going to use the third row. That's what you said, right? So I'm going to basically write that out. Tell me the sign of the position of that 3. Positive, okay? So that's going to be 3 times, and can't we do this one as we sit? Second. Minus 4 plus 10 is 6. Okay. All right. Let me open a parenthesis there. Okay, now, still using row 3, but now we're going to move to column 3 because that's 0. Remember, that's our friend here. So we're going to do this one. What's the sign of that 1? Positive, so I'm not going to write down a plus 1. I'm just going to put a plus, and then let's do this matrix. And what does that become? Say that one more time, I missed it. Which is 9. Okay. Now let's do the math. Negative 5 times 18 plus 9. This isn't looking good. That's 27 times negative 5. And that's 35. Negative 135. Yes, look at that. Man. We didn't make any dumb errors anywhere. And what I choose you to do is look at that, and you'll see they did it a completely different way, and still got the same answer. Okay? So, I'm not saying mine was any better, but y'all saw the process. Pick something. Okay? They happen to choose to go with row 2 at the very beginning. I've already wiped that out, rather than row 4. And that may have made their life a little easier. I don't know. But if it did, good for them. Okay? I don't see theirs is any that much shorter than ours. I think it's okay. And guess what? We're through with 3.2. Homework exercises here. Any of the odds 1 through 19. Do either 21 or 23 or both. Any of the odds 25 through 35. Think through 37. That's true, false. You won't see many of those on the test, but think through that. Make sure you understand why it's what it is. Then do either 39 or 41 or both. And then I'll let you choose what you want to do of the rest of them. Any of the odds 43 through 47. Okay? You can do one or more of those. Or none of them if you choose. But especially if you're going into this kind of stuff, as in becoming a math major, that might not be a bad thing to look at. Okay. No, actually 45 is just a good one to do anyway. I would definitely do 45. The proofs, I'll let you decide whether you're going to do. Okay. Any questions? Let's move on to 3.3. Any questions on 3.2 before I leave it? Okay. All right. 3.3, properties of determinants. There's a little bit of me that says, why didn't we talk about these before? But there may be a reason. Let's do it. In this section, you'll learn several important properties of determinants. You will begin by considering the determinants of a product of two matrices. So let's start with two matrices. Here's matrix A good old 3 by 3, 1, negative 2, 2, 0, 3, 2, and 1, 0, 1. And another matrix B, their second favorite, 2, 0, 1, 0, minus 1, minus 2, and 3, 1, minus 2. All right. They want us to consider several things. The first, what is the determinant of A? Now, how would you go about determining the determinant of A? You tell me. Say again? First column looks like a good way to do it. First column, third row, pay your money, take your choice. You've already paid your money, so you took your choice. We'll use the first column. Okay? And since we'll start with the first row also, that's going to be, and what's the sign of that upper left? Positive, so that's just going to be a 1. I won't even bother to write that down. What's the determinant of what's left? 3. Okay, that was pretty easy. All right, now, we're still going to use the first column, but this time we're going to go to the third row, because that middle row I can do, it has a 0. Okay. All right. Now, what do we have? What's the sign of the bottom one? Positive, okay, so it's going to be plus, and then what's the determinant of what's left? Negative 10. Okay, and this will be a negative 10. Okay, we've got it, so what is that determinant? Negative 7. All right, next they ask for the determinant of B. And how would you approach this one? Again, you got a couple choices. I see. In fact, you got 4 good choices here. I'll let you decide which one you want to choose. I like the second column, okay? So we're going to wipe that out. Whoa, don't wipe that out, though. Okay. Second column. Okay. I can do the first row. Got it, done, 0. Okay, so let's go to the second one. What is the sign of the position where that negative 1 is? Positive, so that's going to be a minus 1 times the determinant of what's left over. Can you do that determinant in your head? Not times. Minus 3. That would be what? Negative 7. All right. Okay, now let me wipe out all those construction lines here. Okay. This time we'll do the 1 down here. What's the sign of that position? Negative. So it's going to be a negative 1 times. And what's the determinant of that one? Say again? Negative 4. Okay, because of that 0 there. Okay? So, now let's do the calculations. What's that first one? 7 plus 4, 11. Okay. Now, because I don't always trust myself, I want to make sure. Negative 7, positive 11. Got it. Okay. Now, the next thing they ask us for is sort of a boo-hiss here, because they ask us for the determinant of the product of the two matrices, which means we have to take the product of the two matrices. Boy, that's been a while, hasn't it? Okay, so do you remember how to do that? Now, I'm just going to pretend those are next to each other and we're doing a product. Yeah, multiply the thing, yeah. Just like taking a product of anything. Have two big numbers there, you take product of this number times all those, this one by all those, that one by all those. You're doing products of everything. That's what we're doing here too, and adding some of them together. So what size is that? Can you do that multiplication? Yes. What will this be? The size? 3 by 3. Okay. Okay. So let's start. Where do you want to start? First row, first column. That would be a 2. So you still got 2. 6 plus 6 is 8. Okay. Which one now? Second row, first column. Is that the one you want to do now?
Well, next over to 8.
That one? That's it. The first row, second column. Okay, first row, second column. That would be a 0. Like that. 2. Okay, 4. Agree so far? Whoa. Goodness gracious, get out of there. Okay. Next. Okay, that will be a 4. That will be 5. Back to 1, right? Okay. Next. Second row, first column. Okay. 6. All right. That one was pretty easy. A couple of 0. Ooh, ugly 6 up. Okay. Next. Okay.
0.
Negative 3. Plus 2. Negative 3 plus 2. Negative 1. Later, am I going to be able to tell that's a 6? I think so. Okay, next. Okay.
So 0, negative 6, negative 4, negative 10.
Negative 10. Next. Third row, first column, that was 7.
Yeah, so it's 2, 0, 3,
5. Okay. Okay. Next. Third row, second column.
0, 0, 1.
All right, that one was easy. And one we've been waiting for.
Third row, third column.
Okay.
1, 0, negative 2, negative 1.
-1. Okay, so there's AB. And what did they want us to do? Find the determinant of AB. Now that's a little bit messier, isn't it? It's a 3 by 3. It's No zeros in sight. I don't see anything that's really a nice multiple of anything else. We could do our expansion. That's not going to be too bad. We could do one row reduction and see what we can do with that. What do you want to do? Your choice. You paid your money. What you want to do?
So what are we having on 0?
What's that?
I said, what are we aiming for?
Okay. If we do any row reductions, you want to get some zeros in there. I can only see one. I can see a couple of things that will give us 1 0. So if you want to do that, we can go for one of those. I can't see something that's going to give us 2 or more zeros. So hang that one up. Or you could just do an expansion here. I would not do the row or column. I would do the adding the 2 rows. It might be a little bit longer, but it reduces, at least for me, the chances of errors. You know, so that's a pretty simple process. So what you want to do? Try to create a 0 or expand and calculate. So again, expand and calculate. Okay. I'm going to clean up a little bit just because it's so messy. I've got to get rid of this, so since I'm doing that, I'm going to get rid of these lines here because they are nothing but confusing now. They just gave us references on where we were. Ooh, that one's going to be tough, isn't it? Yeah, I got it. That one. Still an ugly 6, isn't it? I'll get rid of that. I don't like it. Okay, that's a 6. Okay, and then we'll do an 8, 6, 5, and a 4, -1, 1. Okay? Now let's do our expansion. So what we're doing now is the determinant of AB. Do your down diagonals first. What would the first one be? You're multiplying the down diagonal. 8. You got it. Do the next down diagonal. A little bit messier, but still doable. Yes, -200. And then your last down diagonal, +6, right? Now, are those down diagonals in your way, or can I do the up diagonals and you not be confused? Okay, let's do that one. Okay, except the up diagonals are negative. Downs are positive, ups are negatives. A negative times a -5 is +5. Okay? This one would be?
So are we doing a -1 times -10?
Okay, you can do that. You can think of it that way. I just think of it's going to be a minus whatever that product is. And what's that product? Minus, yeah, any down diagonals are pluses and up diagonals are minuses.
Okay, so -80?
Yeah, +80. Okay? And then one more. Okay. Yeah, +24. All right. Okay. Now, you got a bunch of little numbers and one big negative number. So let's see what those add to. That would be 104, right? 24 and 80 is 104. And then we're adding to that an 11. So 104 and 11 would be 115.
What is that? What is it again?
Just adding the positives together, any way you want to.
Those are like that's one problem.
Yeah,
Like two
yeah.
problems.
These are 6 sums that you add, 3 down diagonals and 3 up diagonals with the signs appropriate, okay? So that was, if you got a calculator, you can use that. That's 104 plus 11 is 115 plus 8. 115 plus 8. Huh? Well, what answer did you get? Negative what? 77. Okay. Now,
I know we were like adding all that together.
yeah, adding the positive and subtracting the negatives. Okay. I wonder if you did 8 and 6 is 14 and 24 would be 38 and 80 would be 1.
I did.
However you do it. Oh,
I
these
did
two.
6,
Oh yeah, why not?
6, 24.
That would be 30 and 80 is 111. Yeah. And
110 minus
Yeah.
200 is 90, and then 90 minus.
yes, exactly.
In the calculator.
So you get negative 7. Yeah, use the calculator would be another option. Okay. Slows you down, but it's okay. All right. So you get negative 77. Now what do you notice here? The determinant of the product is the product of the determinant. Oh wow! Now is that just true for this one, these two that we happen to pick out of random, or the book did? I don't think so. I think this may be an actual. Whoa, we're over. Actual thing, and sure enough, theorem 3.5 says if A and B are square matrices of order n, then the determinant of the product is the product of the determinants. Okay? So we have illustrated that. We didn't prove it. They do a proof later. I'll let you follow that up if you want to. And we will begin next time with, well, actually, we'll begin a little earlier. No. I think I'll do a paragraph earlier. Oh, no, actually, we'll start at the top of that next page, 121. Let's see, did we get far enough that we could do any exercises in 3.3? I think you can do any of the odds 1 through 5. And we'll stop there. All right. I should have said this before Marcus left, because I'm afraid he'll show up next week, but I want you all to know, good news, bad news situation, right? The good news is next week is spring break. The bad news is we won't be meeting any. Okay? Get over it. Okay? All right. So we'll see you in 2 weeks, almost.
I see him dead.
Oh, yeah, I'll see both of you later. That's right. I should have saved that for later. I'll say it again. Don't worry. I'm really corny. Okay. Take care. All righty.